This is a talk about some recent work in reinforcement learning. I think before I move ahead with the technical part of the talk, I just want to express that the technical and both, let's say opinion part of this talk doesn't have a specific business relevance, and that is what allows me to accept this invitation to speak here today. So just trying to keep that line intact. Okay, great. So this is a talk about reinforcement learning, and that's gained a lot of salience and notoriety recently for its applications in game playing systems like AlphaGo, and some continuous control tasks like bipedal locomotion and various web services applications. I think that reinforcement learning should be contrasted with classical optimal control, where you hypothesize a dynamics model, treat that as a constraint, and then you minimize a cost function subject to your dynamics constraints, which are known. In reinforcement learning, typically you do not know the dynamics model and instead are only able to observe realizations of the state through querying a sort of like a black box transition model. And so in that way, reinforcement learning has a lot in common with simulation optimization or black box optimization. And we can think of it as you have some autonomous agent or control system, and it needs to select some actions, and then this black box environment informs how good or bad that action was, not with some long-term cost of how good the overall trajectory was, but just with respect to that specific action. And then the environment causes a transition to a new state. And so then this process keeps on repeating. Okay, so more formally, this can be mathematically encapsulated by a Markov decision process. There's a laundry list of components of an MDP, such as the state space, which defines where the system trajectories evolve. The action spaces, say in the case of this dog, it's go left, go right, jump up or down. And then there's a state transition model, which defines a conditional density for every state and every action that you start from. You transition to a new state, S prime, that is Markovian in the current state action pair. And there's this reward function, which is defined over state action pairs and maps to the reals. And so I mentioned the the environment provides these one-step rewards. In this talk, we're going to focus on something called the infinite horizon discounted setting. And for that setting, what you do is you define this quantity called the value function, which just takes these instantaneous rewards for each state action pair. We sum them over all time. We multiply by a discount factor with the intuition that things in the future are less valuable than they are right now. And then we compute the expectation over the randomness associated with the state transitions. But it turns out to also be mathematically advantageous to allow actions to be chosen according to a stationary distribution, which is a map from states to actions called a policy. So that stationary distribution, this policy, you also need to compute the expectation over. And so this policy pi then parameterizes the value for every given initial state S. Okay, so that's like the preliminaries. And the general goal in reinforcement learning is to just select the action sequence that gives you the most value. So in the case of a reward function, you're looking at long-term cash flow, or in the case of going to some goal location, you are trying to minimize the distance to that goal, even though you don't know exactly how to get there. So these are just like two instances off the top of my head. Okay, so now that we have the technical guts of the setting clear, what happens if we try to apply some of the recent state-of-the-art techniques in reinforcement learning? So if you combine some methods based off of approximate dynamic programming or Q-learning with some neural network parameterizations. That's called a deep Q network. And you can apply this on a variety of different environments. I think the main thing I want to point out is that in order to obtain some reasonable notion of convergence, you need a lot of training epochs. So each of these training epochs contains like 1,000 state action pairs. So what this means is that the x-axis is on the order of millions. So that's one thing. And another thing is like we have these very high error bars, kind of very volatile. So we see high sample complexity and high variance. So that is if you try to go through an approach based off of trying to solve Bellman's equations, also known as dynamic programming and its various approximations. The story is very similar if you try to instead do something based off of stochastic gradient ascent directly with respect to your policy parameters. So let me move this up here, over here actually. So the point is if you take like trust region policy optimization, policy gradient method, or proximal policy optimization and apply that for a variety of settings. So you again see this phenomenon where the x-axis is on the order of millions, and in order to get convergence. And importantly, still we have this like high volatility issue in the course of the evolution of the value function across time as a function of the policy parameters changing. So I think the point is like whether you start from trying to approximate the optimal value function or you try to directly do policy search, either way, we have this issue of sample inefficiency and high variance. So that has led to a sort of emerging collection of techniques to try to address these issues. But I think before we get into them, it's important to just scratch our heads a little bit about where is this like volatility and sample inefficiency coming from. So it could be that just like the transition dynamics of the system are very jittery. So in the case of like classical like particle physics, we see these kind of things happen. But I think in a lot of the problems we care about related to continuous control, like the world is not that jittery. It's essentially deterministic in bipedal locomotion, but still we have this problem. Another issue is that the reward function could just be very sparse, aka it's zero at a majority of the state action pairs you visit. So it takes a very long time before you ever figure out like what is the quote like being on the right track mean. And I think intimately related to that is that these algorithms are often run from like cold start, which means that the policy is initialized with like a very, very like naive priors, often uninformative. And so then there's just like a lot of jitters as like these algorithms try random things in order to like maybe hit the jackpot of like finding that sparse reward. So I think my like inductive bias is that these second two issues are much more important than the first one. But nonetheless, I think all of them are related to the question of like how should we think about improving the reliability of returns and the sample efficiency of return in practice. And so, we've seen a lot of experimental approaches to define algorithms that are exploration seeking or are risk averse or seek to alleviate this issue of the uninformative prior policy by like having access to an expert or some collection of demonstrations that the RL agent should try to imitate. So there's a lot of like experimental work going on in these areas, but not that much in the form of like, let's say, conceptual understanding of what is similar and different about them. So that's what I want to focus on in today's talk. So I think the important thing to note is as soon as we go beyond the usual definition of the value function, then the sort of Markovian structure of the state transition dynamics, a sort of like additivity of probability measures with respect to Bellman's equation breaks. So we have something called time inconsistency when we look at, for example, the variance of the return, or other broader decision-making goals. So people have thought a lot about how to derive algorithms to solve generalizations of the value function in the operations research community. And I would say they've hinged upon either trying to solve modified versions of Bellman's equations, more generically multi-stage stochastic programming approaches. And I think they're theoretically interesting, but they haven't led to very many practical algorithms that actually like can handle the problems we care about. I also want to give a call out to Bayesian and distributional RL, which rather than just trying to track the expected cumulative return, try to track the full distribution of returns. And I think those approaches are interesting, but they run into all of the challenges we face in approximate Bayesian inference when we consider state spaces defined by inferring hidden neural network parameters. So I think they're interesting, but it's I would say it's still an active area of research, and best practices is actively being sussed out. So I'm going to focus on a relatively different approach today, which is like how to define a generalization of the value function that can lead to efficient reinforcement learning algorithms that lead to like polynomial time solvers for this generalization. And the point is that this general utility, which is a generalization of the value function I've been talking about, it actually subsumes several of the aforementioned goals, like the exploration problem, the learning from demonstration problem, and the variance problem, if we consider very specific definitions of these quantities. So let's get into that. Okay, so I'm going to start by building on an LP generalization of the LP reformulation of Bellman's equations, and that'll be directly applicable only to the tabular setting. And then we'll show how this kind of reasoning applies more broadly to parameterized settings, so as to apply to larger state and action spaces. Okay, good. Okay, so let's quickly go through some of how in the tabular case, solving for the optimal value function can be reformulated as the Bellman optimality equation, which can then be re-expressed in terms of a linear program. Okay, so Bellman's equation, Bellman's optimality equation has this form, and it basically says that the optimal value starting from one state is the max of the one-step reward plus the max of the value starting from another state in expectation over the state transition dynamics. Now, I think dating back to some management science works in the 70s, this could be reformulated as a linear program. I think it's most lucidly explained in this 03 paper, where they say that, or where it's derived that this fixed point equation can be reformulated as an LP, where the objective is an inner product between an arbitrary non-negative vector and the value concatenated over the full state space. And then there's a constraint, which is basically let's say a linear matrix inequality reformulation of Bellman's equation. So nothing too fancy there. And here I'm writing this piece of A as just a representation of the transition dynamics as a transition matrix over the state space, across the state space. Okay, and so in the Peterman textbook, you can find some very nice exposition regarding the dual of the derivation of the dual of this LP. And the dual of this LP now is a maximization problem. Lambda are our dual variables. And it's interesting here that the dual variables are what's called unnormalized state action occupancy measures. So these dual variables, lambda, just take the probability of being in a given state action pair and sum it across all time. And we need a discounted factor because we're in the discounted setting. And again, we have a constraint in the dual LP, which is related to Bellman's equation. So you can think of this sort of like a conservation of probability flow. Okay, and so I said that these occupancy measures are unnormalized, and it's important to note that you can recover the policy through normalization for any given state action pair. Okay, good. So that's the dual LP. And now let's get to how we can actually define a generalization of the value function that is solvable in polynomial time. Well, before, let's move this back. Before we had just this first inner product term between occupancy measures and the reward concatenated over the state space. And what we propose doing is adding to it any convex function, convex function of the occupancy measure. When we maximize the negative, it's concave. And so then rather than being linear, now it's concave. Okay, so then rather than this being an LP, now it's a concave program still in the space of lambda. Now, it's important to note that we can't actually solve these LPs like we do classically with the simplex method because we don't actually know what this transition matrix is. As I mentioned at the beginning, it's a very different setting from classical optimal control where we know how the system dynamics evolve. So because we don't know this state transition matrix, then the constraint becomes stochastic. So is this a problem? Well, if we have access to simulate, let's say, a generative model or some simulation oracle that gives us state action pairs, then we can come up with an iterative stochastic approximation method to solve it. And so that's exactly what we're going to do. We're going to look at this problem, we're going to derive its Lagrangian relaxation, we're going to derive a stochastic primal-dual method for it, and the stochastic approximation is required to deal with this state transition matrix being unknown. So that's what's going to happen next. But before I get into that, I just want to quickly comment that this convex function of lambda is very meaningful in the context of the instances I mentioned before. So in particular, if we consider the inner product between the occupancy measure and the reward, this is just the usual value function. But if we define the entropy over the state space, then this has been associated with the maximum entropy exploration problem, which has been used recently to try to handle this sort of sparse reward issue I was describing before. And let's say there are generalizations of this objective I don't want to get into. And there are also objectives related to imitation learning. If we say, okay, we have access to some prior policy, from that we can construct its associated occupancy measure, and then we can just look at the KL divergence between our current occupancy measure and this, let's call it informed prior demonstration occupancy measure. So these three different potential criteria can all be underlined by objectives of this form. Okay, so now that we've got our bearings on how this looks like for a couple practical instances, let's go into our solution methodology. And I sort of, are there any questions?
So just a clarification, because you had also mentioned risk-sensitive MDPs earlier. Can this type of convex function of the occupancy measure also capture consistent risk measures, or other than the entropic risk which you mentioned?
Yeah, I think that's a good. That's a good question. Let's go back to the instances. So we can consider the variance, for example, like inner product between lambda r minus the square of that quantity, total quantity squared. That I believe becomes non-convex. In the paper, we do analyze the non-convex case, but the like the formal guarantees are a little weaker in that case. That's comment number one. I think comment number two is that there are some risk measures that are still convex. Like I think there is like a lot of coherent risk measures are convex in a certain argument, but when you write out their instantiation in terms of occupancy measures, they become non-convex. So that was sort of a confounding observation that we haven't yet been able to overcome. But I think it's an interesting avenue of future research for sure. And especially, and there's a related question, which is like, how does the risk actually the definition of risk you consider propagate into how this like, what do you call it? Conservation of probability flow constraint. And that we haven't dealt with either. So I think these are two open questions associated with this problem.
Okay, thanks.
Yeah, that was a nice question. Okay, so just getting into some of the solution methodology guts, I sort of gave away the story here. So we're going to formulate the Lagrangian of this problem, and then because we don't know this transition dynamics, we're going to consider stochastic approximation, and so that is exactly what our algorithm does. It solves this saddle point method by doing alternating, let's say, descent steps with the value vector and ascent steps with respect to the unnormalized occupancy measure. Since the occupancy measure is an unnormalized distribution, it turns out to be like numerically as well as like theoretically advantageous to consider a mirror ascent type update for lambda. And so we consider that which uses the Kale divergence as the Bregman divergence. I mean, there's some technicalities related to refining the radius of convergence that motivate doing that, as well as like improve numerical performance practice. Okay, so this is what the algorithm looks like, and yeah, as long as we can sample trajectories and get access to rewards, then the algorithm proceeds by doing stochastic descent steps in the value vector and stochastic ascent steps with respect to the occupancy measure. But the reason that this expression looks a little more intricate is because it's actually a stochastic mirror ascent step with a Kale divergence as the Bregman divergence. And then at the end of the day, we can obtain the normalized occupancy measure just by dividing by its one norm on that. Is because lambda unnormalized is non-negative. Okay, good. So at the end of t iterations, we output their recursive averages, and if you do that, then you can show that you know, the duality gap has this to obtain an epsilon optimal solution. You need capital T iterations, which is at least like linear. Let's call it log linear. And the cardinality of the state action space, and this, but this is to, and so then as you have this convergence in the duality gap, then you can translate this to convergence in terms of constraint violation and suboptimality. And so I should mention, I guess there's a lot of, I don't want to call it like chest puffery. Let's just call it, there's a lot of lingo these days about when do you have global optimality and global convergence. So yes, because this is a concave program, then the sub-optimality you're converging to here is global, and the rate is from any initialization point. So it's global convergence to global optimality, and same with the constraint violation. Okay, just to clarify. So here's a couple, like a quick numerical examples to just like illuminate that this works in the tabular setting. So here's here's like a navigation problem where you're starting off here to the left and you're trying to go to this reward over here. And so this is a sparse reward problem. And the reward is more negative in the dark green and less negative in the light green. So you can see that up here is the low risk path and down here is the high risk path, in the sense that like if you hit this dark green, then the reward you're going to get from going to the goal is nullified. And so if you do just a standard Q learning or a standard risk neutral LP solver, what you obtain is a policy that will always take you down this path. But if you use the variance, as I mentioned before, to Aditya, then the policy will result in always following this path. And so you can sort of like corroborate this intuition more quantitatively by looking at the mean of the cumulative return for the risk neutral versus the risk averse setting, and see that the mean of the cumulative return for the risk sensitive one goes up more slowly, but it eventually reaches the same point. But if we squint at this, it sort of seems like it's wiggling around less. And this can be more quantitatively illuminated by pointing out that the risk averse one has lower variance of the cumulative return as compared to the risk neutral one. Okay, so that's like a quick sanity check showing that this does what it's supposed to. And we have some corroborating evidence for the problem of keeping, let's say, adhering to some prior demonstrations. So in this problem, it's a similar like navigation problem in the tabular setting where you're trying to go to this goal. And if you start with prior demonstrations, then the algorithm converges. Then the algorithm, I guess what the way to interpret risk averse is the one that is like adhering to the prior demonstrations. And the point is, like, if you adhere to those demonstrations, then the mean of the cumulative return is much higher earlier on in training. And then here we just track the percentage of trajectories that the algorithm is like crashing into this negative reward dark green part. And for the one that's adhering to the prior demonstrations, then this doesn't happen much, but the one that has to do sort of like cold start and find its own way hits this dark green part quite a lot before converging to something reasonable in terms of returns. So I guess this is like a quantitative way of saying that it's like not good to be left to make one's own mistakes. And like if you can follow the expert, then like, yeah, you can avoid some pain in eventually getting to a reasonable operating point. Like that's my intuitive takeaway from this example. Okay, good. So here we just do some quick comparisons to some competing techniques, and we just want to illuminate that the variance of our method ends up being much tighter around the accumulated reward than the alternatives. Okay, so that's all for the tabular setting. We've got a decent amount of time, so I'll try to do my best to give fair treatment to the parameterized setting, but I just want to admit, or let's say like caution, that it's much more, let's say like technically intricate. So for our point of inflection, like we proposed a new notion, a new general utility, which is like any concave function of the occupancy measure. And we proposed solving it by appealing to the linear program reformulation of the dual LP for Bellman's optimality equation. We derive some sample complexities for the algorithm to achieve global optimality. And we showed some simple examples that suggest that this definition of a general utility is potentially useful. But the major drawback of what we propose so far, which is a drawback of any LP approach to RL, is that the decision variable has dimension, like lambda has dimension s times a. So, and this is true of pretty much any tabular RL solver. So as these state space and action space become large, then pretty much any like algorithmic update becomes inoperable. So how to deal with this? Well, we're gonna do something that is not too surprising for those familiar with reinforcement learning. We're gonna propose parameterizing the policy using some parameters theta. But we're not going to do it in the standard way. We're going to define a parameterization in terms of the occupancy measure. Okay, so what do I mean by that? Well, let's revisit our definition of lambda. It's just the long-term sum of the probability of being in a given state and action conditioned on the fact that actions are chosen according to some policy, pi. So before we said pi is defined for every state action pair, but now we're going to say pi is defined in terms of some parameter vector theta, which is in RP. Okay, so then this lambda becomes a function of pi theta as well. So then before we were trying to solve this function, this general utility function with a representation of lambda for every state action pair, now we are going to reorient it to instead be an optimization problem over parameter space theta, which is an RP. And we're going to look at lambda as a function of pi, which is a function of theta. So there's sort of a compositional structure or like reasoning to what's going on here. The technical challenge is that even though things were concave in lambda, now they become non-concave in theta. So it's not it's not a direct path from here. So we can't just go for the standard like concave programming approach that we had before. So then we need to think a little bit about how do we want to do parameterized policy search with respect to pi theta. Before I get into those technical guts, I just want to make a quick comment that a lot of the related works, like for example, about maximum entropy exploration, are focused on the tabular setting. Efforts to look at like imitation or remaining close to a reference policy mostly are establishing convergence to stationarity. And most approaches to constrained MDPs are only able to show convergence to local KKT points. Okay, so this issue of non-concavity in the policy parameters theta seems to be serious, especially in just the general parameterized setting, not imposing any specific structure on the parameterization. So I think that's what we're going to do a little bit differently, is to impose some specific structure on that parameterization. So in particular, by viewing the occupancy measure as a function of theta, we can draw some direct connections between classical policy gradient theorem and how it looks like for this general utility. Okay, so for the classical policy gradient theorem, okay, when we just have the value function as the cumulative return, then the gradient of the policy parameters with respect to the value function has this specific form where which is a product of factors. There's this score function, or the gradient of the log of your policy, and this Q function. And so as soon as you have this policy gradient, then you can think, oh, I can use this to derive like first order stochastic gradient method or deterministic if I knew what the state transition dynamics were. Okay, but this is invalid for the general utilities because the Q function is not well defined. But we can still follow some similar approaches to derive something that can be used for policy search. Okay, so for the general utility, we just follow what we know from Calc 1, which is we apply the chain rule to derive the fact that the general utility is a product of factors. There's this first factor, which is the partial derivative of the general utility with respect to the occupancy measure. Then there's the gradient of the occupancy measure with respect to the policy parameters. So what's going to follow next is we're going to use this first factor here to try to define something that is a Q function like object. And we call that the shadow Q function, and then its instantaneous, its instantaneous samples, we call those shadow rewards, much in the same way that the Q function up here is an expected sum of rewards, and it's a function of theta. Here, this what we're going to call the shadow Q function is also a function of theta. Okay. So what's going to happen next? Well, so the key to our approach is we note that this general utility is a concave function of lambda. So therefore, it can be numerically advantageous to replace f by its convex conjugate. And that is inspired by a lot by how the conjugate gradient theorem is derived. And then once we look in the conjugate, the dual variables associated with that conjugate, we can look at a first order perturbation analysis in the parameter space and then allow the length of that perturbation to go to 0. And if you do that, then you end up with, sorry, this expression is long, with a legitimate expression for the policy gradient of the general utility. And so as I mentioned before, there's the Fenkel conjugate of the general utility. There's this perturbation vector x. There's this perturbation length delta. This is going to 0. And then there's this v of theta semicolon z. Now this looks strange, but this is just the inner product of the dual variables in our occupancy measure. And so, yeah, this looks like a complicated expression, but it actually leads us to have an ability to actually compute or have a formula to compute the gradient of the general utility with respect to the policy parameters in terms of any nonlinear function of lambda, the occupancy measure. Okay, so so let me try to just get through some of the intuition for how this works and what does the algorithm look like, because I think we're going to run out of time if I go into too many details. Okay, so first I want to explain why did we look at the conjugate of the general utility. Well, it allows us to define these dual variables z, which we call the shadow reward, and they if the general utility is just the cumulative return, then the Fenkel dual is 0 and the shadow reward is equal to the usual reward. So that's, I think, sanity check number 1 that should be encouraging. If we consider the entropy maximization problem, then the Fenkel conjugate has this explicit form, and then the shadow reward has this specific expression. So what I think is interesting is that the shadow reward initially for the entropy maximization problem, if you start near the center, is just suggests that it's equally rewarding to go in all directions. But as you explore more and more, then it's only rewarding to go further and further away from the starting point. So I think that's an interesting observation in practice. Okay, so that's just some instantiations of what this dual variable z, aka the shadow reward, actually looks like in 2 specific instances. But now, if we actually want to estimate the policy gradient for the general utility, you note that there is a min-max thing going on. So, we, similar to before, we need to do a stochastic primal-dual gradient descent and ascent thing. So now, if we are given access to a trajectory following some fixed policy, then we can estimate the shadow rewards like this. This is directly coming from the expression for the variational policy gradient. And then we need to update our perturbation vector x, which is in policy space. And then at the end of running this algorithm, then x is going to converge to our estimate for the gradient of the general utility. Okay. So here's just like a quick diagram of what this algorithm actually looks like. You get access to your trajectories. You compute your shadow rewards, and you do your perturbation vector x, which at the end of the day gives you your estimate for your gradient with respect to the general utility. Okay, so all this is just for the gradient estimation part. And then the question is like, how should we actually use this for reinforcement learning? Well, of course, then we just ran projected gradient ascent steps with respect to using our new gradient estimator. And then this is how we will have new policy parameters, say to form the mean of a Gaussian. And then we'll follow that policy for a little bit, generate another batch of data, and then this process repeats. So this starts to look a lot more like a regular reinforcement learning algorithmic framework. But now it's important to note that we have this additional shadow reward thing going on, and that is used to construct this like alternative way of doing the gradient estimate. Okay, good. So now I just want to go into a few comments about the theoretical analysis. So one thing we can show is that under some specific assumptions, specifically that there's a bijection between occupancy measures and policies, then this non-concave maximization problem with respect to theta actually has no spurious stationary points. So in particular, this maximum, this maximizer is, or every first order stationary point of this problem is a global maximizer. Okay, so that's interesting comment number one. Interesting comment number two is if we consider a version of our algorithm where there's zero gradient estimation error due to, let's say, subsampling. So this is sort of an idealized analysis. Just how good is the quality of our asymptotic gradient estimator? Well, if we run an iterative policy gradient ascent scheme, then it will actually converge to the globally optimal solution of this problem. And additionally, if the general utility is strongly concave, then you get a sharper convergence rate. Okay, so I think it's important to ask, like, how is this even possible for a non-concave maximization problem? And I sort of alluded to this already with the bijection between the occupancy measure and the policy space. So in particular, if we reorient our thinking in terms of lambda again, then this problem can be sort of be thought of as allowing policy parameter updates to instead define parameter updates in terms of lambda, and then it was concave in lambda. So that's sort of the intuition. And so we can think, okay, we're actually doing movement in theta space, but because we have the some specific conditions related to the bijection between occupancy measures and theta, then it's able to arrive to the optimal lambda, which then, because it was concave in lambda, we're good. Okay, good. So that's what's going on at a technical level, and I think I could probably save more of the like mathematical guts for the Q&A afterwards. I just want to quickly wrap up with some experiments showing how this looks like for the maximum entropy exploration problem, as well as, what's the other one, as a constrained MDP problem. So this is OpenAI Frozen Lake. What we do is we visualize the world model here. The white parts are like the gaps, or like the frozen part of the lake that, like, if you go there, you'll fall in. And if you try to solve this as a maximum entropy exploration problem, what you're really trying to do is just figure out where in the world is not the frozen lake. So if you follow a uniform policy, you'll end up with a reward, with a policy that looks like this. But if you follow a maximum entropy policy, then you'll end up with a policy that looks like this. And so we use variational policy gradient to solve for a maximum entropy policy. What I really wanted to illuminate here is by solving this problem, it constructs this shadow reward or like incentive structure for this problem, which shows that clearly there's no like entropy or information to be gained by going in the frozen part, but then there is bits of information contained everywhere else. So I think that's pretty interesting. Here's just some quick plots showing that the entropy of our algorithm actually does increase to some value that's much larger than a uniform policy. And this right here is just a validation that the gradient estimator associated with the variational policy gradient formula is actually converging to the right thing. So we just compute the cosine similarity of our gradient estimate to one that is obtained with like a brute force, a very long horizon Monte Carlo rollout, and show that the cosine similarity is eventually converging to one, and that this is happening across a variety of different general utilities. Okay, good. So that's that example. Probably I don't have time to go into the constrained MDP setting, but I will say that we just consider a general utility defined by putting a logarithmic barrier for a constraint function that is like defining some cost. And then we did experiments with like different selections of the penalty parameter. And what we can see is that you obtain like globally optimal solutions for, but of course now they're functions of the penalty parameter. So I think there's a natural extension of this work as trying to figure out how should we employ the occupancy measure parameterizations to solve constrained MDPs using hidden concavity. So I'll just like make that comment and move on to try to wrap up since we're out of time. Okay. So reinforcement learning has had led to some significant technological feats recently. It has these persistent experimental issues of large sample complexity and high variance during training. And that's led people to really dig in on the experimental side on trying to reduce the volatility through like risk sensitive methods, exploration problems, and incorporating prior demonstrations. But those methodologies were in often cases missing conceptual like underpinnings. So we propose a way to unify them through concave functions of the occupancy measure. And we developed ways to solve this in the tabular and the parameterized setting. We provide some simple proof of concept experiments suggesting that that they may work for some of the larger scale problems we see leading technology today. And I think there's a lot of natural next steps for that. So I'm happy to take questions.
Well, thank you, Alec, for the very interesting talk.